All right. Hello. My name is Marcel Moore. I'm from Porous from the University of Oslo, and I would like to welcome you to this third edition of the Porous Media Tea Time Talks. We're starting our careers as YouTubers here, so you saw that our attempt at the countdown didn't quite work this time, but we're working on it to make it better next time, okay? So I'm joined here today by the Tea Time Talks team, Maya Ruke from the Imperial College London, Kamal Singh from Heriot-Watt University, and Mohammad Noura from the Oslo University. And also Tom Trace is joining us in spirit as he's enjoying his well-deserved vacation these days. So first of all, I'd like to really thank you for all the very positive feedback that we've been getting. I mean, we're really putting quite a lot of effort into making this webinar series and making it regular. So it's really good to hear all the nice things that you've been saying, especially in this depressing COVID time. So thank you very much. This series is meant to be complementary to the geoenergy and geoscience webinar, and you can find that on our featured channels. So today's sessions will be shared by Maya and Mohammad. But before I move on straight to the session, I would like to remind everyone that Interpore registrations are now open. And all of us in the team are very grateful to Interpore. I mean, it's been very important for our careers and for ourselves in many ways, and it is very important. And I think many of us have met through Interpore, so this is very good. And you can register for this year's conference. It's going to be online. And to register, you go to interpore.org, and then you see this page here. And then you click on this big, great Interpore 2020 banner there. And then you go to the next page, and there is a button there, registration is now open. So I think the fees have been dramatically reduced. So it's really nice. And I'm sure it's going to be a very interesting online event, especially I think it's especially important for the early career researchers among us, because it's very good. Interpore is great for us to have a good overview of how big the field is. And that matters a lot, especially to the early career ones. Okay, so I think with that, I will finish opening this session. I want to remind you that you can ask questions anytime for the speakers. You can just type them in the comment field on YouTube, so you don't have to wait for the end of the presentations. You're not going to distract the speakers or anything, because the chairs will gather the questions and then the chairs will ask them at the end. So let's move on to Maya, who will chair the first session. Thank you.
Okay, thank you very much, Marcel. The first speaker today is Eseosa Ekanem. She is a PhD student at Imperial College, and her work involves the use of microfluidics to investigate the complex rheological behaviors associated with EOR viscoelastic polymers for single-phase flow and porous media.
Hello, everyone. Thank you, Maya, for the introduction. So today I'm just going to be talking about the visualization of viscoelastic polymer solution in porous media using microfluidics. So in trying to understand the behavior of viscoelastic material, we want to understand them in terms of their rheology. And rheology has to do with the response of a fluid to a certain form of deformation. When we classify fluids, we classify them as Newtonian fluids or non-Newtonian fluids. For viscoelastic fluids, they are under the category of non-Newtonian fluids, meaning that their viscosity varies with shear rate or the rate of deformation. For viscoelastic fluids, they behave as though they are viscous liquid or an elastic solid. An example of such fluid is hydrolyzed polyacrylamide, HPAM, which is a copolymer of acrylamide and acrylic acid. If you look at the movie on the right-hand side, this is an example. This is the HPAM in the bottle. You can see that the viscous behavior of the fluid allows the fluid to flow out of the glass jar. However, the elastic behavior is what makes it go back into the glass jar, depending on the kind of shear that is being imposed on the fluid. So how do we understand the rheology of this viscoelastic polymer solution in porous media? So if you look at this figure here, it represents a porous media structure whereby you're having a convergent divergent geometry, because porous media is a series of convergent divergent geometries of like different pore throats and pore bodies. So imagine you have a polymer solution whereby the chains are in solution. When they get close to like in contraction, they tend to stretch and their rheology output will definitely change. And so when you carry out the characterization, you see that the rheology changes whereby we are experiencing the viscosity reducing as the shear rate is increasing. And then it gets to a critical shear rate and the viscosity begins to increase. This region here is called the shear thinning or the pseudoplastic behavior. And here is the extensional, is the dilatant behavior or shear thickening behavior. We also found that at this critical shear rate, if you look at the pressure drop as a function of the velocity or the shear rate, there's an increase in a change in the pressure drop. So we find out that the pressure drop relationship with the velocity is nonlinear. And in this same shear thickening region, we have also found that we experience some form of turbulence. But this turbulence is not related to the Newtonian turbulence, turbulence for a Newtonian fluid. It's more like an elastic turbulence because the Reynolds number is below 1. So then what is the complexity? So a lot of people have looked at this fluid in different kind of porous media structures. Like Kawale et al. Has looked at it in, tried to look at it in staggered squares, geometry, circles, just trying to replicate what you see in a porous media. And also they et al. Has looked at different solid fraction of the porous media structure, and they kind of visualize the flow fields, and they realize that we're still seeing the same thing, whereby the pressure drop is non-linear and the viscosity is changing, the rheology is changing. So what are we trying to do in our own case? What we're trying to do is to go back down to a simple system, such as a single contraction microtunnel, where we just have a single pore body pulse rate system. And we use this system as a microfluidic channel. We use it to understand the flow, the flow fields as it moves from the inlet to the outlet, which is going from left to right. So the microchannel here has pressure sensors embedded, which can help us to understand what the pressure is or how the pressure changes, and we image the contraction area just with the use of particle image velocimetry techniques so that we can be able to understand the flow fields as well. So in the long run, we compare the flow fields from the velocity and look at the pressure and see how that impacts the elastic turbulence. So the fluid we use here is HPM, like I initially mentioned, which is a viscoelastic polymer. We use this concentration, the molecular weight is quite high, and we have salt injected into this fluid. And then we estimate the relative apparent viscosity first with this equation. We use a dimensionless number instead of the shear rate because it better characterizes our fluid, and then we estimate the normal stress. So the data you see at the top here is our results for analysis from the pressure drop, and at the bottom is the analysis from the imaging the velocity flow fields. So you can see that when we plot our relative apparent viscosity as a function of the Browne number, you see the same change in rheological behavior as well. You see that the pressure drop is nonlinear, and the normal stresses as well increases at the points where we begin to see that there's a change towards a shear thickening behavior. If you look at the velocities as well, you see that at the Browne number of 0.05, which we are in this region here, we believe that this region here, the fluid is more Newtonian-like, and the symmetry of the fluid is the fluid is very, very symmetric. If you keep on moving on to the Browne number of 0.5 and 5, you see that the flow fields are beginning to change, and then you see that at the Browne number of 5, the flow field is a lot more unstable, and here you begin to see that there's a turbulence. So we decided to go on to analyze the velocity streamlines along the entire the span of the rheology. And so you see that at the Browne number of 0.05 from our movies, we see this symmetry in the velocity fields. And then as you keep on going increasing the Browne number, see at the Browne number of 0.1, where we think that we are starting to see the shear thickening coming into play, the flow fields begin to change, and you can see that continuously as you go to the Browne number of 0.5. When we get into the Browne number of 2, we begin to see that the elasticity of the polymer is coming into play, because you can see the flow fields are beginning to bend. And then when you go to the Browne number of 3, we begin to see more of the vortices, some primary and secondary vortices happening here. And then the flow begins to become chaotic and very unstable. You see that when you're well in the shear thickening region, around 5, 7, and 10, the flow is very unstable. So we decided to try to understand this fluctuation. So the first thing we did was to look at the velocity fluctuations. On the y-axis here is the normalized velocity fluctuation, as a function of the channel length. So what we did was to take the velocity in the center line of the channel and then plot it as a function of the channel length. And then you see that for the run above 7, which is the shear thickening region, you can see how the fluctuations are a lot more compared to the run above 0.5, where we're in the shear thickening region. And then after, this line here represents the contraction, the throat. And then you can see that downstream of the throat, the flow field and the velocity is a lot more, it's not as high as you expect in the upstream. So we see that the fluctuations are upstream, more upstream than downstream. We went on further to look at the pressure fluctuations. We plotted the pressure drop as a function of time. And you can see that the pressure is fluctuating systematically as the run number increases. And we went on further to look at analyze the fluctuations at this high the run number region using the power spectral density. So with this, we computed it via the fast Fourier transform, and then we plotted the power spectrum as a function of the frequency. And what you see here is a decay in the power spectrum. So we did this for all the Deborah number cases, and you can see that the decay, which is an exponent beta, was plotted as a function of the Deborah number just to see how this decay happens. So you see that the exponent is increasing up to a point, and then it becomes flat. So what you see here, Kolmogorov turbulence represents the turbulence for a Newtonian fluid. You can see that the turbulence we're experiencing is not, it's a lot higher than you expect for a Newtonian fluid. We also think that the fluctuations we see in this kind of structure is spatial and temporal. So what happens here is that what we try to do here is that we try to use the velocity, the image velocity flow fields. We take the center line of the channel over the space of 0 to 4.4 millimeters, and then we compute it over the time of the experiment, which was about 0 to less than 5 milliseconds. And what you see here is that you don't see so much fluctuations. You don't see fluctuations in this Deborah number of 0.05. But then when you get Deborah number of 3, you can see that the fluctuations are moving within space, and they are moving over time as well. So this kind of fluctuations are spatial and temporal as well. So in order for us to further understand what is happening in this channel, what we did was to try to use the flow topology parameter to understand how this fluctuations happen. And we use that with the flow type parameter. This flow type parameter uses this rate of deformation tensors and this omega, which is also known as the vorticity tensors. So with this kind of parameter, we're able to know locally where we're experiencing a purely rotational kinematics, shear kinematics, and extensional kinematics. So the first thing we did was to use a base case and try to see how this topology parameter QF works for a Newtonian fluid like glycerol and water. So you can see here at the flow rate of 50 microliters per minute, the velocity flow fields are very symmetric. We don't have any form of fluctuations. Then when you look at the topology parameter, you see that most of the parameter upstream is a lot more extensional and downstream is extensional. Then we went on to look at it for our own fluid HPAM. You can see that at the Deborah number of 0.05, where we were experiencing a symmetric flow field similar to the Newtonian fluid, you can see that the topology parameter looks very similar. But then again, when you begin to increase the Deborah number to 0.5, we see that the shear kinematics begin to take precedence and the extensional kinematics kind of reduces. But then we see it more in the Deborah number 3 and 5, where we think we are more in the elastic turbulence regime. You also see that in topology, the topology histogram, where we see a shift from 1 towards 0 and -1 for these cases. So we do think that the reason for this elastic turbulence is because of the shear flow. So where the viscoelastic normal stresses are happening in shear flow region. So in conclusion, I'd say that we've been able to show that this elastic instability happens in this single contraction channel without any complexity of the multiple portrait systems that we have seen, and that the elastic turbulence is more due to the fluids because the fluid is viscoelastic, and it happens, and the normal stresses increases, and so this happens in shear flow, and the fluctuations are actually spatial and temporal in nature. If you want to know more about what we did in this work, you can check out our recent paper, which we published at Physical Review E. And then thank you for listening. I'll be happy to take any questions now.
Thank you, Eseosa, for this great presentation. And I would like to mention that everyone who wants to ask a question can type it in the comment section. For the starter, I would like to ask a question. And Eseosa, would you please give us more detail about the quantification of the streamlines and which methods have you used for the tracking of velocity and the tracking of the liquids within the system?
Okay, so like I said, we use the particle image velocimetry technique, and for us to be able to understand to get the flow fields, the lines that you see that I showed in the slides, we use the method we use MATLAB. We use a PIV lab tool on MATLAB to be able to track those velocities that you see in the slides.
Thank you. Our first question is from the Rate the Himalaya. Fantastic work. I was wondering if there is an array of throats or multiple throats connected to a pore, and what would be the effect on flow field and shear thinning behavior?
That's a very good question. So presently, what we are working on is trying to look at different multiple throat systems, because there's the assumption that in a situation where you have multiple pore system, the flow fields these fluctuations in the flow fields will definitely increase, and it's due to the fact that the polymer solutions do not have enough time to relax before they get to the next pore if the portraits are close to each other. And then if the portraits are far away from each other, they may still have enough time and will not experience this increase in shear thickening. So it all depends on the closeness of the pore throat. It also depends on the contraction ratio, which is the ratio between the width of the pore body and the pore throat. So all those things play a role in affecting how the shear thinning and the shear thickening transition happens as well.
Very well. Next question by Rayhana Akbari. Is it possible to describe your system in terms of viscous and capillary forces and their mutual impacts?
Well, some people I've seen papers whereby they have tried to look at it, but like I said, it all depends on the size of the device. So you might probably see this viscous capillary forces in channels that are maybe, say, channel contraction ratios that are very small. But in my own case, you might not really see this because of the change in contraction ratio between the size of the pore body to the pore throat. Yeah.
Very well. Next question from Right the Himalaya. I was wondering if you are planning to introduce a second immiscible phase during flow, like co-injection or something like that.
No, I haven't considered that. So what I've been working on is just single phase flow, because this kind of polymer solutions are very complex. So the first thing I was trying to do is to understand how the behavior of these viscoelastic polymers are first, before introducing another complexity of having a second fluid.
And the last question from Michael John. Thank you for your talk. I would like to know if there is a numerical work associated to this work, considering the shear thinning viscoelastic fluid model.
So I'm not really a computational person. I haven't done any computational work on this, but I know that I have seen a recent paper whereby they have looked at the computational work as well. So, yeah.
Okay. I guess we have another question from Right the Himalaya, and it will be last. Final question, what would be the effect of surface roughness?
Well, the microfluidic channel is relatively flat. It's relatively flat, so we do not consider any effect of roughness. Yeah, but yeah, I'll just put it like that.
Very well. I would like to thank you again, Eseosa, for your time, for this great talk, and for the nice visualizations. We wish you luck with your future work. And now we move on to the second talk of this session by Mohammad Masoudi. Mohammad is a PhD research fellow at the Department of Geosciences, University of Oslo. In his PhD, he is trying to have a better understanding of near wellbore processes during carbon capture, utilization, and storage, CCUS, by numerical modeling across different scales. Today, Mohammad is going to talk about Pore-scale reactive transport and the importance of probabilistic nature of nucleation and crystal growth in porous media research. Thank you, Mohammad, for joining us today, and floor is yours.
Hello, everyone. Welcome to my talk. Thank you, Mohammad, for the introduction. I'm Mohammad Masoudi from University of Oslo, Department of Geosciences. And today I'm happy to talk about Pore-scale modeling of nucleation and growth in porous media with a probabilistic approach. Today I mostly talk about these two papers, which I will share their link in the comment section afterwards. The first one is the kinetic control on the distribution of secondary precipitates during CO2 basalt interaction, presented in the International Association of Geochemistry Conference, which is about the idea of probabilistic nucleation. And the second one is Pore-scale modeling of nucleation and growth in porous media, which is about the probabilistic model of nucleation. Precipitation occurs in many different geological processes, such as CO2 sequestration, sediment diagenesis, hydrothermal circulation, and some other formation damage processes. And in all these cases, it's so important for us to know where, when, and how these secondary precipitates form, because precipitation of minerals affects the hydrodynamic properties of the porous media, such as permeability. For example, consider this typical Singapore system and its velocity field. If this darker gray mineral want to precipitate in this system, the position of them makes a huge difference in the velocity field. If it precipitates in the throat, we see a big difference in velocity and a dramatic decrease in permeability. But the precipitation in the pore makes no difference. And in both of these cases, nucleation is the first step of precipitation, which is overlooked in many reactive transport simulators. And now we are going to talk about the nucleation. There are other references that suggested that the nucleation process is probabilistic, which you can find in our paper. But this idea popped up in our head when our team did this test. They injected seawater and CO2 in a basaltic glass column at high temperature. And basaltic glass offers a reasonable chemically homogeneous substrate surface with high reactivity. And the dark color makes it easy to see the formation of secondary carbonate phases. This work demonstrates that few and large crystals formed at random locations along the basaltic column. And this can only be explained in terms of an overall control of mineral nucleation. So we decided to develop a new probabilistic approach for modeling nucleation process. We develop a new model which is based on classical nucleation theory. In classical nucleation theory, the induction time is defined with this equation, which is a function of temperature, supersaturation ratio, interfacial free energy between the nucleating phase and the substrate, and also nucleation rate constant. In our model, the induction time is considered as the random variable, and it statistically spreads around the measured or reported induction time, tau n, and this tau n can be obtained from experiments, or in our case, it can be calculated from the classical nucleation theory. To find the probabilistic induction time, a random number, which is normally distributed between 0 and 1, is generated, and the value of tau p, or the probabilistic induction time, is found such that the value of the normalized cumulative distribution function, this f, at this time is equal to p. And this procedure is repeated in every time step, and we assume that one stable nucleus forms for each induction time longer than the time step. We implemented this model in a Pore-scale lattice Boltzmann-based reactive transport simulator called Yantra. Yantra is an open source reactive transport simulator, which is coupled with a geochemical solver called Frixie. And we made this domain, which is 2 millimeter to 1 millimeter with the grid resolution of 10 micrometer. And supersaturated solution enters the domain from the left-hand side. And top and bottom are no flux boundary, and the outlet is zero flux, zero diffusive flux boundary condition. We simulated two systems. The first one is this single component idealized mineral system, and the second one is calcite nucleation and growth. We studied the effect of solution supersaturation, growth rate, and flow rate on the pattern of precipitation of mineral A in porous media. We also compared the probabilistic and deterministic approach for nucleation. And there are lots of things to talk about, but there is no time, and I only want to show you the comparison of probabilistic and nucleation case, probabilistic and deterministic case. As you can see here, there is no nucleation in deterministic case after 45 minutes of simulation time. Because for the deterministic case, the deterministic induction time is around 70 minutes for this case. So there is no nucleation event at 45 minutes. And at times of 90 minutes and 135 minutes, you can see that there is less precipitation here compared to the probabilistic case. The reason is that in the probabilistic case, the nucleation might form at time much sooner than the deterministic induction time because of the probabilistic nature of the process. For example, in this case, the first nucleus formed 12 minutes after the simulation started. And it's clear that it has more time to grow and form new crystals. Another difference is that between these two cases is that in deterministic nucleation, the nuclei have covered all part of the substrates, which is not the case in the probabilistic simulation. And also here it's more uniform. And as you can see here, for the deterministic case, when the nucleation occurs, nuclei form everywhere on the substrates, and a region with lower supersaturation ratio forms around all the substrate, and this layer is developed during the simulation, as you can see here. The formation of this layer everywhere around the substrate causes a more uniform growth of the precipitates. In the probabilistic approach, however, because the nucleus form at different times and different places, the formation of this low supersaturation layer is not uniform. So it's affecting the nucleation time, and also it prevents more nucleation events around the previous nucleations, and also it causes the non-uniform patterns for the probabilistic approach. And in terms of permeability, if you compare these black circles with these green ones, we can see that using the deterministic approach, the change in permeability will be underestimated. So in summary, it's so important to consider the right physics of nucleation process if we want to have a correct estimation of the change in morphology and the hydrodynamic of porous media. And we are currently developing a proper clogging model using this probabilistic approach. Thank you so much, and I will be happy to answer any question.
Thank you very much, Mohammad, for the great presentation. We have already some questions here. The first one is by Raihane. What is the grain size and the throat size in your system? What about the time steps, number of components sent to the geochemical solver, and computational resources to handle such systems?
The grain size and the throat size, as you can see here, I really, let me show you. Okay. The system is, here is better. Okay. The system is 2 millimeter to 1 millimeter. So the grain size might be, I don't know, let's say 10, if the resolution is 10 micrometer, maybe 100 or micrometer something. But the thing is, it doesn't matter. We generated this system, a random porous media, to see if our model works, if our model can see what we have seen in the laboratory. So it really doesn't matter for us, and it's a small system using lattice Boltzmann. And if about the second question, for this system, the number of elements sent to the geochemical solver is only one, because as she mentioned, this kind of simulation needs high resources, and we use this NREC, which is Norwegian clouds for researchers. We use that, which provides us some supercomputers to do these simulations. And we use this this idealized single system to decrease the simulation time.
Okay, thank you. There's one more. Thank you for the very nice talk. Do you have any experimental data to compare with the probabilistic and deterministic approaches?
Yes, we have some experimental data. It's not to compare with but it's not for comparing probabilistic and deterministic approach, is to show that that nucleation is a probabilistic approach. And also, when I mentioned here that this tau n, this induction time, this measured induction time, can be measured in a laboratory or can be calculated with this equation. We also have some experiments done in our team and done with Mohammad Masoudi to get this induction time and the number of the crystals in with the experiments. Yeah.
Okay, thank you. There's another question again from Raihane. Can you use both approaches for CCS and geothermal problems? Which one is closer to reality?
This is something that we are currently working on. This is a work in progress. It's a really good question, because in CCS the reactions are too fast. We really need to run some models and do some experiments to answer this question. As I mentioned, this is something that we are currently working on, and maybe in 1 month we can answer it. Hopefully in 1 month we can answer it.
This sounds great. Okay, then I would like to thank you again for the great talk, and also Eseosa for her great talk. If you want to learn more about the work from the presenters, we will post their corresponding publications in the comments later. The next session is the 11th of August at 10:30 in the morning again. This time we're gonna have 3 speakers from 2 different institutions giving us 2 presentations, one on pressure tomography for CO2 plume monitoring and the other one on termite mound constructions. Yeah, we are very much looking forward to see you there again. If you have any questions, comments, or feedback, feel free to post something in the comment section or to email us at porous-media@gmail.com. We also sent around an email reminder. So if you wish to be added to the distribution list, just drop us an email mentioning distribution list in the heading. Yeah, then thank you very much for listening. We're looking forward to seeing you again in 2 weeks' time.